Good evening, loyal viewers. It is March 20th of 2020, day 3 of Honors Physics for COVID-19, and we are wrapping up everything we have learned in the past 3 weeks about voltage, current, and resistance. Familiarize yourself with the different places you can find DC and AC voltage if you need it, and pay attention to how environmentally friendly some of these sources are and where the steam comes from to turn those turbines if you're making AC. Remember that when we say voltage, we usually mean voltage difference. 9 volts to 9 volts doesn't do anything, gang. You need a high voltage and a low voltage in order for current to flow. Investigate why people can't sit on telephone wires like birds do. And conventional current flows from high voltage to low voltage, treating electric potential energy like gravitational potential energy. Of course, the electrons actually flow the other way from low voltage to high voltage, and really the electrons aren't going much of anywhere. It's the electric field that's going all around, which is why we're going to just stick with conventional current. If you don't have a complete circuit with a way in and a way out, you're not going to get any current. Current flows to the path of least resistance. If one branch of the circuit has higher resistance and one branch of the circuit has lower resistance, you're going to get more current in the branch with lower resistance. Look up the 4 variables that affect the resistance of a material. You cannot change the resistance of an ohmic material from what it says on the case unless you've got a chainsaw to chop up the length, decrease or increase the width, and probably you'll need a nuclear reaction or a trip to Hogwarts if you want to change it from one material into another. We've got several different equations for power. I squared R tells you how hot you can expect the wire to get. V squared over R takes power down to first principles. Yes, you can change the power rating of an ohmic material from what it says on the case. Saying that it expects to use 1100 watts of power is only true if you've plugged it in the good old US of A at 120 volts, the way the manufacturers expected you to. If you're using a different voltage and you change the resistance, yes, you will totally get a different power rating than the 1100 watts it said on the box. Be an educated consumer that knows something about circuit notation and how to read it. Know the symbols for resistors and variable resistors, for light bulbs and LEDs, diodes, capacitors, inductors, different kinds of grounds, fuses, circuit breakers, and anything else you might actually need in home wiring. Review ground, why no current flows through ground, and why grounding a circuit keeps you safer by a good 50%. Is a short circuit a good thing or a bad thing? Well, it's a terrible thing. A short circuit is a path of little to no resistance. It means you're going to get ridiculously high current in the short. It's going to overheat everything around, melt whatever plastic insulation happens to be knocking around your wires, melt the solder, have things fall because the solder's melting, start fires, you name it, and worse, it diverts current from the things you actually want to work. So not only do you set fire to the lab bench, the appliance still doesn't work because it's still not getting current to the place that matters. Know how a fuse works and how it sacrifices itself to prevent the overheating and electrical fires you saw with circuit breakers. Know that you have to fix the problem before you replace the fuse, and you do have to replace a fuse because a blown fuse is permanent. If you're working with a large appliance or a building, you know the symbol and know why you would be using a circuit breaker rather than a fuse, which can be reset. Review on YouTube how to work an ammeter and how to work a voltmeter, how you should wire up the ammeter, how you should wire an ammeter in series with whatever device you're trying to measure, which means disconnecting the circuit, making that series go straight through the meter all the way from the red lead to the red, red to red for high voltage, black to black for low voltage, and then complete the circuit with the probe like so, to make the current go through the ammeter in order to get to the bulb. When using a voltmeter, you should wire in parallel. That is, make another branch of the circuit right across whatever it is you're doing where you can bypass the appliance and go into the voltmeter. tapping down without making it part of the circuit. You can recognize a series circuit because when you add more elements, more resistors, more appliances, the current goes down because the resistance goes up. In almost all normal circuits, that is to say parallel circuits, where you can have separate branches and you don't have that problem where one goes off, they all go off. When you add more resistors or appliances or devices in parallel, the current goes up. A brownout is what you get when you have too little current because you have too much resistance and then nothing works. A blackout has the exact same symptoms, namely, nothing works and it looks like the power's out. But in this case, the power really is out, not because you have too little current, but because you have so much current that you've tripped your circuit breaker and the circuit breaker has shut off all the current in your house or in your wing of the building to protect things from catching fire. Solve a problem with a blackout, you need to lower the current. Solve a problem with a brownout, you need to raise the current. We'll look at those in the numerical examples. Combination circuits go from the battery and the total current in either direction. If the first thing you hit is a resistor, you are looking at a series circuit with parallel bits. Draw black boxes as many times as you have to in order to get it down to a series. If the first thing you hit in both directions is a junction, that is a parallel circuit with series bits. Draw your black boxes accordingly. We've actually done Kirchhoff's rules in class. We just haven't called them Kirchhoff's rules. We said this was conservation of charge. What goes in must come out. The sum of currents flowing into the junction is equal to the sum of the currents flowing out of the junction. You've been doing this in parallel circuits for ages. Kirchhoff's second rule is the one we call conservation of energy. If you go all the way around a circuit from the bottom to the top, you're going to have a series of voltage drops. They're going to be equal to the voltage boost you get from the chemistry in the battery going from the low end to the high end. So if you start with 9 volts and then you have 3 resistors and a voltage drop of 3, 3, and 3 again, all together, 9 minus 3 minus 3 gives you 0. Now in a circuit with only one AC source or only one battery pack, this is intuitively obvious to even the most casual observer. Kirchhoff's second rule comes into its own when you have interesting systems and networks with multiple voltage sources, and you simply do the conservation of energy going round and round, where everything you hit, this battery here, and IR for this resistor, and IR for that resistor, and whoa, that battery is facing the wrong way, and oh wait, IR for that resistor over here is going to equal 0. If you have a circuit like this with 2 branches, there's 1 square, 2 squares, 3 squares, you get 3 equations, 3 unknowns, and you solve for everything you need to know. For a more complicated network, you will get more boxes, more loops, more equations, more unknowns, fundamental theorem of algebra. Sooner or later, you'll have a system. You can either solve it by hand or into your calculator and have the calculator do it for you.